Thank you for meeting me online. My tummy is just feeling a little off today, so had to switch to online, but I am recording, so I'll post this later. So a couple of extra notes first. There is an extra credit chance. So we have an optional survey from a different university that's just going to ask about your experience in the course. So it is completely optional. You do not have to do it. It'll take about 10 to 15 minutes, but we sent this out to all the pre-cal sections at UTSA, and the survey has also gone out to other universities, and this other school is going to aggregate all the results, and so they're going to share how UTSA students feel they're doing, and then they're going to compare that against how students in other universities feel they're doing with a course that is being administered with a course team. Because we have a whole team of pre-cal instructors who teach this course. So we call that a highly coordinated course. So this is surveying universities that are using this structure. And we're going to use the results to basically say, like, see, this is a good thing. Because there's some university professors who are sticks in the mud who are like, I don't want to be coordinated. And we're like, but you'll have to do less work and your students will be happier about it. So we get some research results published, and then we're like, and now research shows you should do the thing. But be honest, whatever you want to say there is fine. So I'm not going to see your individual results from this survey. It does ask for like a student identification number. You can put in your UTSA ID or your ABC 123. Either one will work. They're just going to share me the list of who completed the survey. Yeah. So this, if you do it, is going to result in an extra dropped web work grade. Now, there is also, totally separate from this, the end of the year survey from UTSA. Those are going to open on Monday. So end of the year course surveys are a little bit different than surveys you may have done in other cases. Like if you've ever had a friend who worked at a fast food place and they're like, hey, can you fill out the survey for me? Just make sure to hit all tens, because they actually get in trouble if they don't get all perfect scores. Like their manager gets a call and then they get their butt chewed out. Our course evaluation surveys are not like that. So I am not going to get in trouble if you don't give me all perfect scores. So it is your chance to be honest about what you liked about the course. So they'll have questions about like, how did you feel the course ranked? Like, was it great? Good, okay. Like it'll have the whole description. And then underneath that, it has free response questions where you can say, was there anything your instructor did that you thought was really good and really helpful? Was there anything they did that you found really bad, unhelpful? Is there anything you wish they did? So that's really your chance to like explain to your professor stuff they did that was good, stuff they did that was bad, and extra stuff they could do that would be really helpful to you. None of us will see the results from that survey until after grades have been posted. So this is also your chance to be completely honest with the professor. So that way you can say, like, every time I asked a question in class, you made me feel stupid. Like, that's a serious thing that professors should pay attention to and should not do to students. And they may not be doing it on purpose. Some professors just have a really weird face when you ask a question that can look very much like a resting bitch face. But it's not that your question is stupid, it's that their brain is trying to process how to answer the question. And, because a lot of college professors are on spectrum. No proof for that, but that's just my pet theory. Answering a question like takes a little more brain power and a little more thinking than they're used to doing. So that's why you get the like weird faces. So course survey results do get read by more than the instructor. But what they don't do is if you have an instructor who's really bad and like everybody in the class rakes him over the coals, and it doesn't have to be a him, it just all of my bad instructors in the past were hims. No, not all of them. Anyway, so everyone in class rakes that professor over the coals. Like they all come up with like, here's things that this person did in class that was really bad. Like, this person like needs to go learn how to teach because they suck. Like someone else in the department will see that. It will get brought up to their supervisor, and the supervisor will be like, all your students are saying you suck. You need to not suck. But if they're tenured, that's about all that can happen. We don't have a like, if you don't improve, you're going to get fired. If they're tenured, they are unfireable. Um, and also, like, college professors don't actually have to get any training in how to teach to be a college professor. Like, even our new employee orientation didn't have hardly anything about how to teach. So, if some of your professors, it feels like they never got taught how to teach, it's literally because they never got taught how to teach. So, um, you know, give them a little bit of like courtesy and respect for that in the way you frame your answers. Because some professors, like, it's literally no one ever told them, hey, don't talk to the board. They can't hear you well when you do that. And like, if they get somebody who says, I can't understand you when you talk to the board, can you please finish what you're writing and then turn around and address the class with what you're saying so I can make sense of it? It's like oh, no one ever pointed that out to me before. Thank you. So now they then have to remember to do that. And that can be, weighing it against years of talking to the board because the board doesn't give them funny faces. So, take it with, it may not have as big an impact as you would like, but sometimes it's literally no one ever told them don't do that. So take what you will from that. I welcome any feedback you want to give me, whatever I do that's good that you like, whatever that I didn't do or that I should have done better, please let me know. I can get a list of who completed the survey separate from whatever your responses are. So I can assign extra credit for doing the course evaluation survey. And for the course evaluation survey, it's going to be a dropped writing assignment. So you've got 2 extra credit chances here. So any questions about either of the surveys here, the research survey or the UTSA course evaluation? All right, so the link for the survey is in the announcements on Canvas. It says extra credit chance. All right, so now our Amplify. We are going to look at exponential and logarithmic functions for the rest of the semester. These will be on the final exam. In fact, the final will kind of have a little more emphasis on these because these are skills you're going to be using in calculus. You need to be actually fairly comfortable with your logarithm properties and solving exponential and log equations. Like you just want to be comfortable solving any equation, and this is just adding some extra equation types to that list of equations you can solve. But before we get into the solving and the properties, we have to understand what the heck we're talking about. Now, if you took college algebra with us or in some algebra course in the past, you should have been introduced to exponential functions and logarithmic functions. So the material we're doing today is going to be treated as more of a review. So we're not going to cover all the slides in the Amplify activity. We're going to skip over some. You're still welcome to do the in-between slides if you want. If you want to use that as a review to remember like what exponential functions and logarithmic functions are all about, like feel free to do that. I'm just cherry picking questions that are similar to what shows up in the web work homework. All right, so our first slide here is just the basic definition of an exponential function. So an exponential function is any function that can be written y equals a times b to the x. So our variable is now the exponent instead of being the base. So when we have a function of this format, if the a value is positive and the b value is between 0 and 1, so like 0.5, a half, or 0.25, a fourth, or 0.729, which is some ugly number. Like any decimal between 0 and 1 as the base of the x power is going to be a decay graph. So it's going to be a decreasing growth. Things are going to get smaller and smaller. Vice versa, if our a again is positive, but the b value is bigger than 1, so if we have like 1.1 to the x, or 2 to the x, or 7 to the x, those are going to be exponential growth functions, where we're going to be growing bigger and bigger and bigger. The big thing for both of these types of graphs, though, is that what we have happening as usually our input variable is time. So it'll be number of seconds or hours or weeks or days or years even, if we're doing like carbon dating. For each increment of time unit, our amount is changing by the same percentage. So this is different from a linear growth. Linear growth is like ticket prices. If I buy one ticket for $5, that's $5. If I buy 10 tickets, that's $50. Each increment of ticket was one more increment of the price. Here, though, it's like the things are changing by a percentage instead of by a fixed amount. So if I'm, doubling after a day, I multiply by 2. Then after the next day, I multiply that result by 2, and then the next result by 2. And so it grows much faster than a simple linear growth. Or if I'm decaying, I'm decreasing, I'd multiply by 0.8 because I'm losing 20%, so I have 80% left. So it's times 0.8 times 0.8 times 0.8, and it'll decrease down. So we're going to flip all the way over here to slide 10 now. Okay. So slide 10, they give us 2 points, and they tell us that this is an exponential function. So this is enough information to solve for the function formula. So I'm going to write down my 2 points. 2, 5. I have 6, 80. And then my basic exponential function formula is f of x equals a times b to the x. So now I can take my point, my xy point, I can put 2 in place of the x, I can put 5 as the function value, and then I will have an equation. So it would look like so 2 for the x and 5 for the function value, 80 for the function value, and 6. So I have 5 equals ab to the second, and then I also have 80 equals ab to the sixth. So now I have 2 equations and I have 2 unknowns, a and b. This is enough information to solve for a and solve for b. Now there's a couple of ways to go from here, but usually what we do in this kind of setup is we do some sort of substitution. So I'm going to solve one of these equations for one of the variables and shove that into the other equation. Now, when I'm picking what variable to solve for, I like to pick variables that don't have exponents. So the a in both of these equations does not have an exponent. So the a is what I want to solve for. So I want to keep a and get rid of everything else. So I'm going to solve the left equation because the numbers are smaller, and I'm going to shove that into the right equation. So I'm going to divide both sides by b squared. So now I have 5 over b squared equals a. And now I'm going to put this in place of a. So I substituted this into the right equation, and I have 80 equals 5 over b squared times b to the 6th. So that b to the 6th, I can think of as b to the 6th over 1. So I can multiply these two fractions now, multiply the tops, multiply the bottoms. But that b to the 6th will be on top, and the b squared is on the bottom. So those two are b's with exponents, so our exponent rules come into play here. So if I have what I think of as upstairs, downstairs, like upstairs, downstairs neighbors don't get along, they've got a negative relationship, so the exponents subtract. But you can also think of it as b squared on the bottom is b times b. B to the 6th on top is b multiplied out 6 times. So I can cancel a b on the bottom with one of the b's on top, and the other b on the bottom with one of the other b's on top. And that leaves us with 4 b's on top. So I'll have the 5 number times b being multiplied 4 times. So 5b to the 4th, and this equals 80 still. Now we'll divide by 5. So now I have 5 goes into 80 16 times, and then I'm going to leave some space, then put my equals and my b to the 4th. Now I need to cancel out the 4th power here. And figuring out how to write this gets a little weird. So normally when we're going to cancel out the 4th exponent, we think of the 4th root. And the only problem with this is there's no 4th root button on the calculator. Now, maybe if you dig into the menu settings somewhere, there might be an X root button. And that might even be a button on your calculator, but using that button can be a little weird. And understanding what the 4th root is equivalent to is actually more powerful and more useful in your future math classes. So when I have something to an exponent and I want to cancel out the exponent, I'm going to raise it to another exponent. So when I have a base to an exponent that then gets raised to another exponent, the exponents multiply. So what I'm thinking here is, what do I multiply 4 by so it would equal 1? So 4 times 1/4, multiplicative reciprocal, would equal 1. So I'm going to raise both sides to the 1/4 power. Now, when we type this on the calculator, we need those parentheses around the 1/4. Now, it turns out 16 is actually a 4th power already, so this works out nicely. But if it was an ugly number, like we would need to know how to type this. But still, if I type in 16, then my caret 1 divided by 4 is in parentheses. The calculator straight up tells me this is 2. Now that I know b equals 2, I'm going to bring it back over here. A equals 5 over 2 squared. So a equals 5 over 4. And now I can finally write my function formula. f of x equals my a value, 5/4, times my b value, 2, raised to the x power, which just happens to be the first response. So whole lot of algebra equation solving work going on here, working with two different equations. So what questions do y'all have on the flow of this work here, all of that craziness? So our next slide is doing the same thing, but it's doing it from a word problem perspective. And this is the way we usually ask this question on the final. It is a free response question on the final. So here we have a laptop was valued at $2,500 in the year 2015. By 2020, its value has depreciated to $800. If the laptop's value continues to drop by the same percentage, what will it be worth by 2024? So I've got values of the laptop. I can see the values are going down. So I do expect my answer to what will it be worth by 2024, it's going to be less than 800, significantly less than 800. But to figure out the exact amount, I want to generate what the exponential function is here. Now, in order to do that, I need ordered pair points on this function. So right now, $2,500 is associated with 2015. I don't want to use an input number of 2015. I can, it's just really messy looking on the calculator. And it's going to give us some really weird A and B values. So usually what we do in these kind of scenarios is we shift our time frame. We're going to redefine what we're calling our starting time. So we do this by redefining what x is, our input variable. So we're looking at years passing by. So our increment of time is in years. So x is going to be a number of years. But we're going to add an extra caveat. Our starting year is 2015. So we're going to call this the number of years since 2015. So when I look at my 2020, the year 2020 is 5 years since 2015. So that would be an input value of 5 with an output value of the $800 they told us. So that's how I get one of my ordered pairs. Now the 2,500 is also part of an ordered pair. But here, that's in the year 2015. So how many years has it been in 2015 since 2015? I know that's a very weird question. So in the year 2015, how many years has it been from 2015? Well, if we're in 2015, we haven't moved from 2015. So we're in the 0th year. So our input number there would be 0. And this is by design. This is actually what we're forcing to happen here. So now the problem is just what we had on the previous page. We've got 2 points. We're going to plug these into the exponential function and solve for the a and the b values. So I plug in 2,500 equals a times b to the 0 power. Haha, b to the 0 power is 1. A times 1 is a. So this actually straight off gives me my a value, which is my initial starting value, sometimes called the principal. Or a lot of times we use exponential functions for when we're calculating interest. So this starting value is often called the principal because it's a money word. Now my other side, I'm going to plug in my 2 numbers. So 800 equals a times b to the 5th. But now I can plug in 2,500 for a. Now we're just going to solve for b. So I divide by 2,500. So I have 8 over 25, leave some space, equals b to the 5th. All right, now I need to use the power that will get rid of the 5th power. So when we're going to raise both sides to an exponent, it has to be the whole entire side in parentheses raised to the exponent. And then the exponent we're going to use is the 1/5 power. So this is going to be an ugly number. But to get the correct ugly number, we need to type it into the calculator as shown. So 8 divided by 25, whoops, I forgot the parentheses. So 8 over 25 in parentheses. So, and then close, raised to the open parentheses 1 divided by 5 and close. We get 0.7962 blah, blah, blah. So now our function formula is the 2,500 for a times 0.796 to the x. Now, we still have one more part of this to answer, though, and we do this on the final as well. We have a follow-up question. What is this laptop going to be worth in 2024? So I don't want to put 2024 in for x. I will get a tiny, ridiculous number. Because I want to remember my x is the number of years since 2015. So 2024 is how many years since 2015. So if I subtract those two, I get 9. So I want to plug in 9 for x. So I'll have 2,500 times the 0.796 number that's still on my calculator raised to the 9th power. Right, so I have my answer raised to the 9th power, and then I'm going to multiply that by 2,500, and I get 321.52. But they said round to the nearest dollar, so $322. And we get an I'm cooking the cat. So the weird part is when you're given year numbers, you very rarely want to use those actual year numbers. Instead, you want to define your 0 as some sort of starting value and define the rest of them in terms of that new 0 year. Now, there are some questions where they're actually going to ask about what's the percentage that you're dropping the value by every year. So we have slightly a little tweak to the exponential formula that helps us account for that percentage. And that's what our next slide has here. So if we have an exponential growth model, then every year we're doing 1 plus the percent increase as a decimal raised to the t power. Or if we have a decay amount, then inside the parentheses, the b value is 1 minus r to the t. So remember, on both of these, normally our exponential function is y equals a times b to the x. So that 1 plus r is the b value. Or in a decay graph, same thing. Or the b value is 1 minus r. So if something is asking about how much, like, what's the percentage being lost every year or the percentage growth every year, we're going to use this 1 plus or 1 minus factor to figure out the percent. Or if a problem tells us the percent increase or percent decrease, we're going to use this setup to generate the formula. Excuse me. So we've got a few like mini examples on the next few slides. We're not going to do all of them, but we'll do most of them. So we have a function provided. F of x equals 245 times 1.12 to the x. And this is giving the number of bacteria in the sample at the end of x days. So when we look at that function, 245 here, f of x equals 245 times 1.12 to the x. So I can see this is growth because my b value is bigger than 1. And so that means if I want to know the percent increase, I have 1 plus r equals 1.12. And I minus the 1. So my r is 0.12. So this is a 12% increase every day. Now the other piece of information, that 245 is the initial population of bacteria. So when we're looking at our statements here, which one is true is basically what it's saying. The initial number of bacteria is 12. No, that's 245. The initial number of bacteria decreases. No, it's increasing. Increases at a rate of 12%. Yes. And then the last statement, the number of bacteria at the end of one day is 245. No. At the start of the first day, it is 245. Or the end of the 0 day, it's 245. So now our next one, we've got a stock price that is worth $360 today. And this stock analyst believes that the stock is going to lose 28% of its value each week for the next 3 weeks. So then we have our equation. V equals 360 times B to the T to model the value of V of the stock after T weeks. What should we use for the B value? So we're told this is going to lose 28%. So this is a decay graph. So in the decay graph, B is 1 minus R. So R is 28%, which is 0.28 as a decimal. So B is 1 minus 0.28, which is 0.72. So questions on how we figured out the B value there, or any of the information so far? All right, our next one is a gym membership model. So the equation M equals 1800 times 1.02 to the T models the number of members M of a gym T years after the gym opens. So when we're looking at that function formula, that 1800 is the number of members who joined when it opened. The 1.02 is our B value. This is a growth. So that's 1 plus R equals 1.02. So R is 0.02, which is 2% growth. So what is my first statement? The membership rates are increasing 20% each year. That is the false statement. So this model shows exponential growth. It does show growth because B is greater than 1. 1,800 members joined the gym when it first opened. Yep, that's our initial value. That's the way to describe that. And then apparently if we plugged in 3 for T and did the calculation, we'd get about 1,910 members. So the 1 plus r versus 1 minus r is giving you just a slightly different way of handling those exponential growth and decay questions if you're provided with the percentage. That is the format I would go with. But you can also just, when you're provided with the percentage, you can, like, if you have your initial value, then after the first time increment, you can manually calculate what the end result would be. And then you have 2 points and you can find the function. So if you don't remember the 1 plus r or 1 minus r, there's still other ways to solve it that look more like what we did at the start of class. And what we did at the start of the class is the traditional way most people present solving for an exponential equation. All right, so questions on exponential equations, their format, or how to solve for those. All right, we're going to skip that one, and now we're going to look at logarithms a bit. So here is one of the best descriptions I have about logarithms, because this is how it feels when I describe them. So we know addition is putting things together. Subtraction is taking parts out. Multiplication is just repeated addition. Division is determining how much of one number is contained in another. That's a measurement perspective. Exponentiation is repeated multiplication. And logarithms undo exponentiation by unfathomable dark sorcery. And I know that sounds like the worst explanation ever, but that really is the best explanation I have for logarithms. So basically, people were doing a bunch of math and they realized exponentiation had to work and worked in a particular way. And then they were like, oh, well, there needs to be a way to undo exponents. So how do we undo exponents? What would that look like? What would the function have to do? And they figured out what the function would have to do based on it having to exist. So logarithms were like, they had to exist and they just decided to call them logarithms. Like, I don't know why logarithm is the word that goes with it, but that's the word we got. But the whole, like, how it works is it has to work this way because that's how exponents work. So it's a very, like, piss poor explanation for how they work. So here is our definition of a logarithm. So we've got some qualifications. One of our qualifications is that the numbers we put inside a logarithm must be positive. And this is coming from the fact that the logarithm is the inverse of an exponential. So if I draw an exponential function, it'll look like that if it's a growth function. So I can see that the domain is everything to the left and everything to the right. So the domain of an exponential function is negative infinity to infinity, all real numbers. But the range ends up being restricted. Because if I'm looking at like 2 to the x, so I can look at 2 to the first, 2 to the second, 2 to the third, those are all going to be positive numbers. When I start looking at the negative exponents, 2 to the negative 1 power is the same as 1 over 2 to the first. 2 to the negative 2 is 1 over 2 squared. So the negative powers just mean to do 1 over and then the number to the positive power. So we get a whole bunch of tiny fractions. So our result, whether we're putting positive exponents or negative exponents, the result is always some positive number. So our range is restricted to 0 to infinity. Now, when we look at the logarithms, our reflected graph along the perfect diagonal is going to have a restricted domain. So the domain for a logarithm is the range of the exponential function. So logarithms can only have positive numbers inside the logarithm. Now the range can be all real numbers. I can get negative y values and positive y values out of a logarithm function. So because of this, logarithms are our third case of a domain restriction. And then we ask that question on the final. We will give you a logarithm function and ask you what the domain of it is, because you need to understand that logarithms aren't a domain of all real numbers. So we'll eventually cover an example of that. But this is now the third major case of domain restrictions. Our first two cases. First way we restrict domain is by dividing by 0. So if I have 1 over x minus 2, then my x can't equal 2. My second type of domain restriction comes from square roots. I can't square root negative numbers. So if I have the square root of x minus 2, then my restriction is going to be from 2 to infinity. 2 is the smallest number I could put in there. If I have the logarithm of x minus 2, I'm going to get a domain restriction of not 2 itself, but really, really close to 2, and everything bigger. So those are our three domain restrictions. But overall here, like this is just one of the things we learned about logarithms, because there has to be an inverse function for exponentials. So logarithms have that domain restriction. So now what we have is log form versus exponential form. So whenever we have an exponential equation or a logarithmic equation, there is a way to transform one of these into the other. Now, most books cover this with this whole like, this thing raised to that equals this, and it's like got these movement arrows, and like it's not wrong, but it's dependent on having the logarithm first in the equation, and like the whole numbers moving around thing. Like if you're dyslexic, the numbers move enough. We don't need to make them move more. So I don't like this format because it's too easy to screw up. What you should understand is what's going on, why this movement works. So when I'm looking at an equation, and then they give us an equation over here, so I'm going to use that as an example. So log base 2 of 8 is equal to 3. So log base 2 is a function, and the inverse of that function is the 2 exponential. So I'm going to use the 2 exponential on both sides of the equation. Now this looks very weird. I am not multiplying by 2. I am writing 2 as a base and both sides of the equation as the exponent. So on each side of the equation, I'm writing 2 to the left side equals 2 to the right side. Now on the left side, the 2 to the log base 2, those undo each other. So we have just 8 left over. And on the other side, we have 2 to the third power. Now, they want us to type this in, but they want us to type it in backwards. So we're going to type in 2 to the third equals 8. All right, now we're going to try another one. Log base 4 of 16 equals 2. So this is going to turn into an exponential form. So when they say convert to exponential form, they're saying write this so it no longer has a logarithm. So they're saying get rid of the logarithm. So my logarithm is base 4. So to get rid of it, I'm going to use the 4 exponential function. Now I'm applying this 4 on both sides on the left of each side. So the same way when we square root both sides of an equation, like we write the square root in a particular way, this has a particular way of writing it. I would not write like 2 caret 4 on the other side. That is not the same as 4 caret 2. Like the order we write these in matters. So 4 to the log base 4, those guys will undo each other. So we'll have equals 16. And then on the other side, it'll be 4 to the second power. So that's what we're going to type. 4 to the second power equals 16. Now our last one is a little bit weirder. So I have log base 6 of the square root of 6 equals 1/2. Log base 6 gets canceled out with the 6 exponential, and whatever I choose to do on one side of the equation, I must do the same thing in the same way on the other side. So this gives us 6 to the 1/2 power equals the square root of 6. And that is true. The square root can be written as the 1/2 power. SQRT 6. So you don't have to do it in the way I'm doing it here, but understanding how logarithms and exponentials undo each other is going to help us solve logarithmic equations and solve weird exponential equations. So you do want to make sense of this, but you don't have to use this for converting between the forms. You can do it the book way just with the moving the stuff around. It's just, to me, that always feels like guess and check and hope and pray. Now, if we can do the conversion one way, we can do the conversion the other way. So that's what we're going to try next. So now they've given us an exponential equation, and they're asking us to generate the logarithmic equation. So now I have 5 to the second equals, I'm going to leave some space and then put my 25. So to write this into log form, I am trying to get rid of the 5 as a base. So to get rid of 5 as the exponential base, I'm going to use the log with 5 as the base. So we read this as log base 5 of 5 squared. And then I have to apply log base 5 on the other side. And again, just like with square roots where we write it in front of each side, we do the same thing with the logarithms. We write it in front of each side. So that's why I keep saying leave some space when I'm writing. Now the log base 5 of 5 squared, that is just going to leave us with a 2. So we have 2 equals log base 5 of 25. Now we want to type this the other way around. So we're going to start with log. Now to get the base as a subscript, we're going to use the underscore key, which is next to the 0 on the keypad. So it's the shift minus, and you'll notice like it moved the log up and my cursor is now a little below. And now the 5 looks under. Then I hit my right arrow, so I'm back on the line. And I need to put parentheses around the 25. Now on the side, it's already calculating that to be 2, but we just need to type in equals 2. So we have typed the full equation. All right, now same song, second verse, but we're going to try it with a weirder looking equation. So we have 10 to the negative 4th equals, leave some space, 1 over 10,000. So my 10 is my base. So to get rid of the exponential form, I need to use logarithm base 10 on both sides. So that's going to leave me with negative 4 equals log base 10 of the 1 over 10,000. So we start with log underscore 10, back up, 1 divided by 10, close the parenthesis, equals negative 4. And then we get a very excited Snoopy that's in the way of the work, though. So again, the book way focuses on moving stuff around. That's not wrong. That doesn't promote understanding of how the functions work together as inverses. And understanding the functional representation here, how inverses cancel each other out, is the far more usable knowledge. All right, so I'm going to clear this. Let's see. Next slides. All right, so I'm going to skip 22 and 23. I'm going to move into 24 here. So this is a definition. So there are some log bases that we use so often, mathematicians decided to get lazy. So the log base that we actually use the most often is log base 10. So they decided, I'm tired of writing base 10. So if I just write log, just know that that means base 10. So this was their first lazy notation. So if we write log of x, that means log base 10 of x. So y equals log of x is equivalent to 10 to the y power equals x. And then on slide 26 here, we have the natural logarithm definition. So the other log base that we use a lot is log base E. E is a naturally occurring constant named after Leonard Euler, but his last name is Euler, so that's why it's an E. Um, so we write that as Ln. Now this is Ln, it is not In or 1n. Now, because people get very confused about this notation and reading it, I write it very particularly. I write it with a capital L and then an N. So this is just when I write natural log, I'm going to write it capital L and then a lowercase n like this. Because I found when I was working problems, when I wrote a lowercase l, every once in a while I would misread it as one n, and then I would screw up the problem. And that happened like enough times that I was like, forget it, no more. We're using a capital L from now on. Okay, here we go. Identifying the domain of a logarithm function. So we talked about this earlier, that logs have a restricted domain. So if I'm given a function like this, and there are questions in your web work that do this, I want to know what is the domain of this. So the domain of log of anything is the thing is strictly greater than 0. So our thing inside the logarithm is x minus 2. So my domain is x minus 2 is greater than 0, which means I add 2 to both sides, and x is greater than 2 is my inequality way. But if I think back to my number line, I'm going to say all the numbers bigger than 2, which as an interval is from 2 to infinity. Infinity will always get the parenthesis, but here we do not have the equal bar, so the 2 is also going to get a parenthesis. So our domain is open parenthesis 2, infinity 2. Or sorry, infinity, close parentheses, said the wrong thing. Let's see. Now we can actually look at the graphs of exponentials and logarithmic functions. We're not going to do this on the final, but they are technically part of the material we're supposed to cover. They have horizontal and vertical shifting the same way all the other functions do. So the x minus h inside lies, that's our left-right shifting. Outside is y value shifting, so up and down. And then our A and our B, A is going to be vertical stretching or compressing because it's outside changing Y values. And then the B value ends up being a horizontal transformer kind of. But generally we just say that's the base of the logarithm. So if B is greater than 1, it's an increasing function. If B is between 0 and 1, the logarithm is decreasing. So this is just looking at what do the variables do to the graph. So our formula up here is x minus h plus log base b of x minus h plus k. So the minus is in my formula. So when I make h positive 2, that has moved my graph right 2. When I make my k value -3, now this looks kind of weird because I didn't really see the graph move down. I saw it stretch kind of weirdly. And that's because the graph here is actually focusing on the x-intercept, but there's this corner point that was, let me put the k back on 0. So at k equals 0, the x-intercept was 3. Now, when I move that down, that point that was at 3 is now down 3 from that. It was at 3, 0. Now it's at 3, -3. It just happened to change the x-intercept to something else. And then our b value, as b gets really big, the graph gets like increases faster and faster, or slower. It's still increasing, but the graph gets closer and closer to the x-axis. Now, as I bring it closer back, I get to 2. It's kind of a nice little upward. And now my 1 point somethings are like getting more and more. 1.1 is like really stretched up. And then 1, we should actually have a vertical line there, but whatever. And now my b value is less than 1. And we can see my logarithm is decreasing. It's a downward slope. So this is just a slide where you can play around and see what's happening to the graph. Now, this last one is practice evaluating logarithms, thinking about what they would equal. So when I'm looking at like the natural log of 1, the natural log of 1 is asking what power of base e will get 1. So what power of e will equal 1? So anything to the 0 power is 1. So the natural log of 1 is 0. When I look at log base 6 of 36, what power of, here, I'm going to move it way up here. So it's right under the question. What power of 6 will get 36? So 6 to what power equals 36? And that should be 6. So 6 to the 6th? Because I said what power, not what do we multiply by. 6 to the 2nd power. So log base 6 of 36 will equal 2 because we need to raise 6 to the 2nd power to equal 36. So those two go together. Our log of 10,000, log is an invisible base 10. So this is asking 10 to what power equals 10,000. Well, 10,000 is 10 to the fourth power. So this is 10 raised to the fourth power is 10,000. So log of 10,000 equals 4. Now I've got a more basic one, log base 2 of 2. So 2 to what power equals 2? So when we have the number 2, what is the invisible power on 2? Yep, 2 to the first power is 2. So log base 2 of 2 is 1. And this means log base b of b is 1. Any b, those guys would always cancel out, and we just have the invisible first power that's on the 2 there. Now our log base 2 of 1/2, a little more interesting. To get 1/2 as a power of 2, that is 1 over 2 to the first. Our over power, that is negative exponents. So 1/2 is the same as 2 to the negative 1 power. All right, now we just got a few more weird ones. So log base 2 of 256. So it turns out 256, if you sit there and divide it by 2, it is actually 2 to the 8th power. This is what I think of as a computer number. Because when you're looking at bits versus bytes, like this is one of the numbers that is how many bits are in a byte. Well, there's 8 bits in a byte, but how many numbers can those 8 bits represent? 256. We usually say that's 0 to 255, though. Now, log base 4 of 64 versus log base 64 of 8. Rail 4 squared is 16. 16 times 4 is 64. So this guy, log base 4 of 64 is 3. So that means apparently log base 64 of 8 is 1/2. So let me think about that. 64 to the 1/2 power is 8. Well, the square root of 64 is 8, and square root is the 1/2 power. So yes, this is also true. And then on our next slide, it actually was grading us as we went through. But if you didn't know where to start, this gave you some reminders on some of the weird rules and just how to interpret one of the basic log slides. There's an extra video that talks about like logarithmic growth and exponential growth if you want to watch it. But that's just our basics on exponentials versus logs, solving for an exponential function, finding the domain of a logarithmic function, and then a little introduction into some of the basic properties of logs. We're going to focus next week on using log properties to expand and compress expressions, because that is a skill you're going to use in Calculus 1. And it's a really powerful skill, but you have to be comfortable using your log properties to make use of that skill. We are like right at time, so I'm going to stop the recording.